Hi everyone, it's Mr. Hamilton here. Today we're going to talk about the laws of force. This is the independent study unit in our course. What I'm going to talk first about is just a few key ideas. Your note should have a little bit more detail than I'm going to give you here. And then we're going to talk about a few examples that we see in this unit. And so the first thing I want to talk about is the inverse square law. And this has to do with the force of gravity. And as we're going to find out, it's not just the force of gravity, it's actually more than that. But we know from what Newton found that the force of gravity is equal to g times the mass of the bigger object times the mass of the smaller object, if we're doing this in relation to a planet and a satellite, for example, divided by r squared. In other words, he found that the force of gravity is proportional to 1 over r squared. And so as we double the radius, for example, then we're going to get r squared, so it's going to be doubling squared, which is going to be a quarter. So as we double the radius, the force of gravity would become a quarter, for example. Coulomb did an experiment that was very similar to that, where he used a torsion balance, and he used charged particles, charged spheres, instead of the force of gravity. And he found something that was very similar to the force of gravity. In fact, he found that the electrostatic force, Fq, was equal to this constant, which we'll get into in a minute. It's named after him, Coulomb's constant, times the two charges, Q1, Q2, divided by the radius squared. And so hopefully you recognize a lot of similarities there. The main similarity is that we have this constant, and then we have these two values. In the first case, it was the values of the masses. In this case, we have the two values of the charges. And so we can calculate the electrostatic force like such. Let's just go ahead and take a moment and define these terms. Fq is the electrostatic force. And that's just the buildup of electrostatic charges, which we've looked at a number of times throughout our high school science time. And then we have K, and K represents Coulomb's constant. You might wonder what that actually is. Coulomb's constant is a value of 9.00 times 10 to the 9 times 10 to the 9 Newton. And because we're not dealing with mass here, the units are going to be Newton meters squared as it was before for G, but it's per Coulomb squared. Now, note that this is 10 to the power of 9, but our G, if you remember, was 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And so you might think here, gravity is actually feels pretty strong on us, but when you start looking at how powerful the constant is, it's much weaker. In fact, it's to the power of 10 to the power of 20 times weaker than the electrostatic force's constant is, which is quite significant. And so this is why gravity is known as the weakest force in the universe. The next value there is Q1 and Q2. And what they represent are the two charges in coulombs. We measure the charge in coulombs, so the electric charge on each object. And last but not least, we have r, which is the distance between their centers. And so when we actually start looking at the difference between gravitational, electric, and magnetic forces, we can actually see that there's a lot similar. In fact, the thing that's most similar about these is that the force is proportional to 1 over the separation distance. That's constant across any of these different forces. So that's the big similarity between them. The key difference is what they can do as far as attracting or repelling. Gravitational, as we know, is obviously only an attractive force. Two objects will attract by that gravitational force. But if we have an electric or magnetic force, we can actually, with both of those, attract or repel. There's a helpful diagram in your textbook on page 284 that just shows some more of these similarities and differences. So we'll look at two key examples from this section now. Page 280, number 5 is the first one we'll look at. Page 280, number 5 says this. Two identical objects have charges plus 6 microcoulombs. Just worth mentioning here, this stands for micro, which means times 10 to the negative 6 microcoulombs and negative 2.0 microcoulombs respectively. When placed a distance d apart, their force of attraction is 2 newtons. If the objects are touched together, then moved to a distance of separation 2d, what will be the new force between them? So let's start here by writing our givens. We're given that we have Q1, doesn't matter what one we call Q1 or Q2. Q1 is 6.0 times 10 to the negative 6 coulombs. Q2 is negative 2.0 times 10 to the negative 6 coulombs. We know that the force, electrostatic force that we have initially is 2.0 newtons. And we know that the distance of separation is d. So r is d. We also know that the k value is 9.00 times 10 to the 9 Newton meters squared per Coulomb squared. Now really what we're after here, because this is two parts, we first need to figure out what that distance d apart is, and then we need to determine when you touch them together and we move it to a distance of twice that, what the new force is. So the required value really is this r value. What is that distance, that d value that they're apart? And so the way we could analyze that and actually come up with a solution is we want to first recognize that the electrostatic force is equal to k times q1 times q2 over r squared. And if we're trying to solve for r, or for d in this case, we need to cross multiply or do the switcheroo, switch what's in the denominator of the one fraction with the numerator on the other side of the equal sign. And we get r squared is equal to k q1 q2 over the force. And actually solving for r has us do this. So we're going to go 9.00 times 10 to the 9 Newton meters squared per Coulomb squared. Going to have to expand this out a little further. Q1 is positive 6.0 times 10 to the negative 6 coulombs. And then Q2 is 2.0 times 10 to the negative 6 coulombs again. Now you'll notice something that I did here. You might think, well, why not negative? And the reason that's not negative is because if we had a negative there, we're clearly going to get a negative answer. And so we're going to put everything in as positive, and then we can talk about it in the end as being an attractive force or a repelling force. But in terms of the magnitudes that we're after, everything can be substituted in positive. So you might want to just note that. Sub all in as positive, and then interpret at the end. So the r value that we find is, we want to keep lots of extra significant digits here to not get a rounding error, 0.232379 meters. And then it's a matter of saying, well, now what happens when you touch them together? Well, whenever we touch two charges together, they distribute the charges evenly between them. So the first thing we want to recognize is that the Q is going to be the same. And so what we're going to do is we're actually going to add these two charges together and divide by 2. We're taking the average of those two charges. So we have one that was positive 6 microcoulombs. We have another that was negative 2.0 microcoulombs. And then we're going to divide those by 2. So the average charge is positive 2.0 microcoulombs. So after they're touched together, that's what the charges are. They're both going to be the same. We know that the radius is going to be 2 times 0.2322379 meters. We know that FQ is what we're trying to solve. And we know K, it's the same as it was above. So we can go ahead and solve that. We just substitute those into this equation. In this case, those two charges are the same, so I'm just going to write them as Q and Q over R squared, and we just need to sub those values in as shown. So the force, electrostatic force, is going to be 9.00 times 10 to the 9 Newton meters squared per Coulomb squared. We're going to multiply that by 2.0 times 10 to the negative 6 coulombs. And we're doing that twice, so you could either put that as a squared, or you could write that out twice like I did here. And then we're going to divide that by 2 times 0.232379 meters squared. Make sure you multiply it by 2 before you square it. So the value that you should arrive at is a value of 0.17 newtons. And we then conclude, therefore, the electrostatic force after being touched is 0.17 newtons. Now, the reason this is so small is because the charges are so small, right? Yes, the constant is large, but the charges typically tend to be very small. Now, you might think there's another way to do that, and you're correct if you think that. The way you would do that, I'm not going to go over the whole method, but I am just going to highlight a couple of things. You could rearrange for R, like we did here, and instead of calculating R there, you could come up with another expression for afterwards, call it FQ, equals KQ times Q divided by R prime squared, where the primes are the new values. And then what you could do is recognize that that is the same as double the original R. And you could find this new electrostatic charge by subbing an expression in for R squared. And so you could replace R squared with this whole expression here, and that would allow you to solve that new electrostatic force directly. I did it this way because I think it's just a little more intuitive to find the distance first, but you could do that as well. The last question I'll look at in this section is page 283, number 10. This question is interesting. It says 2 2-kilogram spheres are attached to each end of a silk thread 1.20 meters long. The spheres are given identical charges. We're not told what they are, they're identical. And the midpoint of the thread is then suspended from a point on the ceiling. The spheres come to rest in equilibrium with their centers 15 centimeters apart. And that makes sense, right? They're going to be apart because they have identical charges. They're going to repel. What is the magnitude of the charge on each sphere? So the first situation that we want to look at is the givens. And in the givens, in a question like this, we want to actually have a diagram so we understand what's happening. We know that there's a 1.20 meter long thread. And what that means in terms of this situation is that each of those threads, when they're attached to those two spheres, are going to be 0.60 meters long, because in total this whole thread is 1.2 meters long. And so we know the mass on each of those is 2 grams, and it's important we have those in SI units, so that's 0.0020 kilograms. We also know that they're 15 centimeters apart. So the distance between the centers of these two objects is 15 centimeters. That means the R value, again, we need to put in SI units, so that's going to be 0.15 meters. So that's all the information we're given. We're given that they're resting in equilibrium. And so one of the things that we could consider here is that if they are in fact in equilibrium, that means that the force that's trying to pull them downwards, I'm just going to look at this one on the left here. There's this force of gravity that's trying to pull it downwards. But there's a whole bunch of other forces acting on that as well. We have this force of tension that's in the actual string. And we also have this electrostatic force that's trying to repel them directly opposite from each other, or away from each other. So we have all three of those forces actually acting on the one on the left, and then the one on the right, they're going to have all three just mirrored on the other side. And so in terms of this one, I'm just going to label some positive directions, positive x, positive y. And what I want to do is I want to determine some angles here. So I think the simplest way to do this is if I just take this triangle and I kind of cut it in half. So I take the left half of that triangle. That's a right triangle. I know this is 0.60 meters, and I know that because this is half the distance, half the separation distance, that's going to be a value of 7.5 centimeters, or 0.075 meters. And so if I have those things, what I can do is I can determine this angle, because that's going to help me with the force of tension. I'm going to call that angle theta. And so I'm obviously onto my analysis part. I haven't really looked at my unknown yet, but let's list that as well. The required value here is the magnitude of the charge. So what is the charge? They're identical, so I'm just calling those Q. So let's continue on now with our analysis. We're now looking at the angle, and because I know the hypotenuse and I know the adjacent side, I can use cosine. So cosine of that angle is the adjacent, which is 0.075, over the hypotenuse, which is 0.60. And then I can take the cos inverse to determine that. And what I arrive at is an angle of 82.82 degrees. So that's my angle that I can use here. Well, what I want to do is I want to break this force of tension up into its components. So there's a component that's in the x direction, and there's a component in the y direction. And so Fty is that, Ftx is this down here, and then this angle here is 82.82 degrees. I haven't drawn that to scale, but hopefully you get the picture of what's going on there. Now what we need to do is look at things in terms of, you guessed it, horizontal and vertical, because those components, as we've always known, are separate from one another. So let's go ahead and look at the horizontal components of this problem. So horizontally, what's happening? Horizontally, we know that the force of tension in the x is equal in magnitude to the force of the electrostatic charge. And because of that, we also know that the force on the electrostatic force is K times Q1 times Q2, which in this case, because the charges are the same, it's Q times Q, or Q squared, divided by R squared. And so if that's my force of tension in the x, I don't know what a couple things are. I don't know what Q is, and I don't know what this is. I can't solve that. So we're stuck. We go to the vertical. We're trying to come up here with two equations with two unknowns. That's the strategy we're after for a question like this. Again, we know that the force of tension in the y is going to be equal in magnitude to the force of gravity. And I know that the force of gravity is just mass times g, small g, because we're assuming that we're close to Earth's surface and that we can simplify it with that. If we weren't close to Earth's surface, we could just use the gm times m over r squared equation, but we can make that assumption in this particular case. So if you look at this, we actually recognize that we know the mass and we know g. We can solve for Fty. But what we can't yet determine is the relationship between Fty and Ftx. So we need to break this down a little bit further because those two variables are not quite the same. I'm going to start with Fty. Fty is, if you look at this, it's the opposite side to the angle of 82.82 degrees. So we have an option of sine or cos. The opposite side is the one we're after, so that's going to be sine. So this is force of tension times sine of our angle, opposite over hypotenuse, is equal to mg. Let's take this a little bit further. We can rearrange to say it's mg divided by sine of theta. Now we have it in terms of the force of tension. In terms of all variables that we know, we can solve that, but then we still can't sub it in yet because we don't have this in terms of force of tension. Because the y is sine, the x has to be cosine. And so we can write this kq squared over r squared. And so now we know what this is, and we can substitute this into the equation. I'm going to do that substitution. You could have solved for the force of tension first. That wouldn't have been a bad idea. But I'm going to substitute it in directly in this particular case. So I'm going to substitute in mg over sine theta times cos theta. There's my substitution right here. And then that's going to be equal to k times q squared over r squared. And I'm trying to determine what q is. So I'm going to now rearrange this equation by just multiplying by a few values. I'm going to multiply by r squared over k. And over here, I'm going to multiply by r squared over k. That's going to cancel out on the right side, and it's going to leave me, it's not going to cancel out the q. It's going to leave me just with q. So what I arrive at is a value of q that's equal to r squared over k times mg cos theta over sine theta. Remember, the order of multiplication and division doesn't matter, so that's probably the easiest way to put it. Notice that is not tan theta. Sine over cos is tan theta, so just be careful with that if you assume that you can write that as tan theta. Yes, you can write it as cotan theta, but you can't put that in your calculator like that, so be careful with that. What you could write that in is over tan theta, so this would be equal to r squared over k times mg over tan theta. That would be equivalent. You don't have to do that, but I just wanted to point that out for those of you who want to make those connections and simplify even further. So now it's just a matter of substituting those values in, which I'll do as the video is paused, and then I will show you the final answer. Before I give a final answer, it's worth noting that you should note that that's a q squared value. So q is going to be the square root of all of that. If you don't do that, you'll get a value that's quite far off of what you should expect. The q value that you arrive at is 7.9 times 10 to the negative 8 coulombs. All right, a very small charge nonetheless, but 7.9 times 10 to the negative 8 coulombs. And so we can conclude, therefore, the charge on each sphere is that. Just a quick side note here, if you had calculated this initial FT, you would have found it to be equal to 0.019775 newtons, a very small force. So you could have done that as well in terms of instead of substituting that whole expression in. So there you go. There's a solution to that. Hopefully that's helpful. All the best as you work through this independent study unit.